Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all students. So earlier we have learned the theory on plate girder, whereby we learned on the failure modes of the plate girders and what is a plate girders itself. Okay, now we are now in the design process of plate girder. So for us to do the design of plate girder, it is better we go all the clauses based on the examples given here. If you can see here, this is the example of plate girder design. Okay, so this is example one. So in this example, okay, in this example, we designed a plate girder in grade S355 steel to carry a characteristic variable load of 150 kilonewton per meter over a span of 20 meter. The compression flange is fully restrained against lateral torsional buckling. So if you can see here, okay, this is the figures of the plate girder. So the plate girder have a 20-meter length and supporting a 150 kilonewton per meter load. And if you can see the vertical line here, okay, this vertical line represent the transverse stiffness of the plate girder. And the transverse stiffness are located at 1.2 meter from the end support of the girder, and the second one at 2.55 meter, and the third one is at 4.15 meter, and the fourth one is at 6.25 meter, and the last one is at 10 meter. And now these examples, which is example 1, is designed for a non-rigid end post plate girder. Because if we learned in our theory just now, we know that we have two types of plate girder. The first one is what we call as a rigid end post, and the second one is what we call as a non-rigid end post. So this, okay, for this one, okay, if you can see here is a non-rigid end post plate girder. So why it is non-rigid end post? Because you can see at the end of the support there is no stiffness. They only have a stiffness here. But if you have a rigid end post, okay, if you have a rigid end post, at the end of the support, you will have another stiffener right on the top of the support. So if you have these two close stiffeners, we will call it as a rigid end post. Okay, class. So just now I have shown you the examples questions. So now, before we start with the design process, let me introduce to you, or let me explain to you what are the design process for the plate girder. So if you look here, we have 5 steps of design process for plate girder. Okay, and the first step is basic dimensioning. So what does it mean by basic dimensioning? So basic dimensioning meaning that you need to propose the section sizes for a plate girder. So you know that the plate girder, so this is your plate girder, okay? So you need to come up with what is the section size for the flange, okay? What are the section size for a web? So basically in the plate girder, so you need to determine the thickness of plate girder web, determine the total width of flange, determine the thickness of flange, check allowable maximum HW/T ratio, which is the slenderness ratio. Okay, so you need to check the allowable maximum because you have to make sure that the size that you propose for the two flanges and the web must lesser than the allowable maximum's HW/TW ratio. So that is what we call as a basic dimensioning. So once you have the basic dimensioning done and you have come up with the proposed sections for your plate girder, Okay, and then what you need to do, you need to classify the sections. Still remember, in our chapter 1, we have classified whether the section is class 1, class 2, or class 3. So in this plate girder, we have to carry out the same step as well, meaning that in the section classification, you still need to classify whether your flanges are class 1 or class 2 or class 3, and your web is class 1, 2, 3, or 4. Okay, so that are the second step. And the third steps, you need to check, okay, whether the proposed sections are required to be checked for a shear buckling resistance or not. Okay, as we know, in beam design, or what we call as a UB sections, it is rarely necessary for us to check for the shear buckling because they are not slender section. But in this particular case, for plate girder, you usually will have a very thin web. So, and you may end up with a slender sections. So when you end up with a slender section, usually this step 3, which is to check for the shear buckling resistance design, you will end up with this answer whereby you need to go for the next step, which is shear buckling resistance check. Okay, so then you need to check the shear buckling resistance check, and the last one you need to do, what you need to do is that you need to check for your transverse web stiffener designs. As you can see in this plate girder, okay, you not been given a section sizes, and then you need to come up with the section size of your plate of your transverse stiffener itself, and then you have to make sure that the transverse stiffener that you propose, okay, the section sizes that you propose for the transverse stiffener are able to carry the 150 kilonewton per meter in helping the plate girder to transfer the load vertically in terms of the shear force. All right. So here are what we call design process for the plate girder. Now let's go to the first step in our design process, which is basic dimensioning. Okay, so in this design process, we wanted to first find the thickness, the section sizes of the web. So meaning that this is your flange. So now we wanted to know what is the section sizes of the web, what is the thickness, okay, and what is the height of the web. Okay, so for you to come out, okay, for you to come up with the thickness of the web and height of the web, because you do not know now, so for you to come up with these sizes, okay, you have to go to clause 8 EC3 part 1.5. Okay, where in this clause is given that the slenderness ratio of the web, which is HW over TW, must be lesser than these equations. Okay, and this equation also has been given in the previous notes. Okay, you can go through the previous lectures, and also you can go through this clause, and also you can also look at your PowerPoint notes. Okay, so you have to make sure that when you wanted to propose this size, which is the height of the web and the thickness of the web, you must make sure that the height of the web ratio must be lesser than these equations. Okay, so now let's go one by one. What are these parameters? So the first one is the height of the web, and this is the thickness of the web, and K is based on the section classifications of your structure. Okay, so if you propose it being class 1, class 2, and class 3, so then you have to come up with the equations whereby K equals to 0.3, 0.4, or 0.55. And FYF is the yield strength of the compression flange. E is your Young's modulus. AW is the area of the web. AC is the area of the compression flange. All right. So now let's go through the whole equations. How can we come up with what is the height of your web and what is the thickness of your web? Okay, so let's proceed with the calculations. Okay, to do that, we need first to assume what is your lambda. Okay, we need to assume your lambda is equivalent to HW over TW, which is this HW over TW. So you assume lambda equals to HW over TW and should be lesser than the equation given K E over FYF. All right, and then you have AW over AC. So once you have done this, when you have the lambda, assuming that lambda is equivalent to HW over TW, all right, so then you need to find what is your AW and AC. So, but in this case, because you do not know what is the area of flange and area of your web, so for these purposes, because you are now guessing the section sizes, so you can say that the area of the web is equivalent to the area of your compression flange. Because your area of web and your area of compression flange is equal, they are equal, then you can assume that this parameter equals to 1. Okay, so here, therefore, you will have HW over TW, okay, which is lesser than, so K we choose as 0.4, which is the plastic resistance utilized, okay, and then your E is given as 210 times 10 to the power of 3 over, and your yield strength given in the equation is grade as 355. So it is 355. And then here square root AW and AC. As I said earlier, you can assuming that the area of flange, okay, the area of flange, okay, which is thickness of flange and the width of flange, the area are similar with the area of your web. So because of you assuming it is similar, then it is become 1. Okay, so once it become 1, so then when you calculate it, you can equivalent to 237. Okay, so meaning that your HW over TW is lesser than 2375. Sorry, 237. Okay, so once you get this 237, okay, so from this from equations, okay, now let's go to the next equation, which is from equations 5.117, okay, from equation 5.117, where these equations is taken, okay, from notes, okay, notes. You can look at the video lecture, and also you can look at your PowerPoint slide, okay, PPT slides, whereby equation 5.117 give you whereby HW is equivalent to lambda MRD over FYD. Okay, so now what is your MRD? So MRD is your total or your design bending moment. Okay, your design bending moment for that particular plate girder. Okay, so how are you going to calculate the MRD? So MRD can be calculated. Okay, MRD can be calculated. Okay, so now you're going to calculate MRD. To calculate MRD, so MRD can be calculated. Okay, so you have those plate girder. Okay, you have those plate girder. We have those plate girder, whereby you have the total load acting on it is 150 kilonewton per meter. Okay, so it's longer than this, okay, which is 20-meter length. It is a 20-meter length. Okay, so now you're going to calculate the design bending moment. Okay, so design bending moment, so loading on the beam, total loading on the beam, MED, is equivalent to 1.5, this is the factor for the live load, times with 150, which is your loading, okay, plus 1.35, this is again the factor for the permanent load, over 100 over 20. So then you will get 232 kilonewton per meter. Okay, so then you will get 232 kilonewton per meter. All right, so when you get the total load here is 232 kilonewton per meter. So 100 is the assumptions of your self weight. Assumptions of your self weight. Okay, so once you have get this, okay, once you have get this, then you can calculate what is your bending moment. So you know that for UDL load, when you have 232 kilonewton per meter, so we have 232 kilonewton per meter. So what did you get is that with the length span of 20 meter, so therefore you will get MED, which is equivalent to 232 times 20, okay, over 8, isn't it? Finally, you will get 11.6 mega Newton meter. All right, so you will, so now your MED is 11.6 mega Newton meter, which is this value. All right, so then you can calculate. So lambda is already calculated, whereby lambda, initially we assume lambda is equivalent to HW over TW. Okay, so now your lambda is 237, okay, times with what is your MRD is being calculated as I'm shown previously, okay, whereby you have calculated and you get 11.6 mega Newton meter. Okay, so then 27, so that you get 11.6 times 10 to the power of 9 over what is your FYD. So you get 355 over 1, okay, divided by your aspect ratio. And finally, you will get 1978 millimeter. Okay, so once you get your HW1978 millimeter, okay, so then the next part is you calculating the, so that is your, what we call it, your height of web. So your height of web now is 1978 millimeter. So then we wanted to know what is your thickness of web. So the thickness of the web is equivalent to HW over lambda. So where we got this equation from? If you still remember in these equations, okay, we have lambda is equivalent to HW over TW. Now, we already have HW, so we wanted to find what is your TW. So you rearrange the equations, then finally you get TW is equivalent to HW over lambda. So what is your HW? So you can put your HW now is 1978 over your lambda is previously calculated as 237, and finally you will get 8.34 millimeter. So 8.34 millimeter, maybe you can round it up it to 9 mm. This is depends. whether you wanted to round up to 8 millimeter, or you wanted to round up to 8.5, 9 mm, or 9.5 is up to you, okay, because you design it and later we will check it. But in my case, I will round up it to 9 mm, okay, 9 mm. Now we have that our height of web is 1978 mm, and thickness of the web we already calculated, and we said it is going to be 9 mm. So down 9 mm. So what we're going to calculate next? Next, we wanted to know the size of the flange. What is the thickness of the flange and what is the width of the flange to complete the basic dimensioning process. Okay, so now we're going to calculate the thickness of flange and also the width of the total flange. So how can we calculate the thickness of flange and the width of the total flange? Okay, so the thickness of flange and the width of total flange, first we can define the thickness of flange. Okay, in this particular case, all right, let me use another color. So in this place, we can have the flange, okay? Flange, as you can, if you still remember, in table in EC3, okay, table 5.1 EC3, we have the two sections, which is one is for roll sections and the other one is for the welded sections. And in our chapter 1, we calculate the C, okay? So in this case, okay, now we are considering it under welded section because plate girder, as you learn from lecture 1, they are separated. So this is the total width of the plate girder. Total width of the flange of the plate girder. And this is the thickness of the flange. So now we're going to calculate what is the total width of flange of the plate girder and the thickness of the flange of the plate girder. So based on table, okay, if you still remember table 5.1, okay, in EC3 part 1.1, okay, if you can see the strength classifications where it is based on the thickness, okay, thickness of your flange. So C over TF, for you to make sure it is in plastic classifications or class 1, it has to be lesser than 9 of the epsilon strain, isn't it? 9 strain. So here we wanted to know what is the thickness of flange and we wanted to know what is the width of flange. So we can have C equivalent to 9 strain thickness of flange. Okay, so what is your strain? Based on the previous examples or based on the previous lecture in chapter 1, or you can refer in table, okay, section classification, 9 times with the 235 over whatever your grade steel, okay, and then times with thickness of flange. So here you can have 9 235 over 355, okay, and then thickness of flange. So finally you will get 7.33 TF. Okay, so now you know your C is equivalent to 7.33 TF, and here also is equivalent to 7.33 TF. So for you to get the total width of the flange, we now ignore the effects of the thickness of web and also the welded sections, okay, because we are designing it, so we assume we ignore this by just considering that the total width is the C1 plus C2, C1 plus C2. So total width, okay, total width of flange, TF, is now given by C1 plus C2, and I just make a note here whereby the assumption for us to calculate the width of the total flange is by saying that we ignore the effect of well width. Okay, we ignore the effect of well width. So just to highlight here, we ignore the effect of well width. So then you know that your C is 7.33 TF. So then you have 7.33 TF plus 7.33 TF, whereby here 7.33 plus 7.33. Then finally you end up with 14.66 TF. Okay, so total width of flange 14.66 TF. And now the area of flange, okay, area of flanges, okay, area of flange is equivalent to 14.66 TF times width TF. Okay, because this is your TF, thickness of flange. So the total area is here, total area is 14. This is the width, 14.66 TF. 14.66 times width thickness of flange. Therefore, you get 14.66 TF times TF, and finally you get 14.66 TF squared. That is your total area, and this is the total width of flange, total area of flange. Okay, class. So now, once we have determined the width of the flange, okay, because we have calculated the width of the flange, so now let's calculate the thickness of the flange. Okay, so for you to calculate the thickness of the flange, okay, you have to refer to our notes, whereby there are several ways in designing the plate girder. So at the moment we are using method 1. So if you are looking at our PowerPoint or our video lecture, okay, the thickness of the, that from equations, 5.111, given that your MPLRD is equivalent to FYD, BF times TF times HW. Okay, so this is, you can get it from notes, okay, notes or video lecture. Okay, so you get this and you rearrange the equations, because now we wanted to know what is the thickness of flange. Okay, so here is representing our area of flange. So MPLRD, okay, we rearrange the equation, divided by HW, and then FYW over gamma M naught, which is the aspect ratio. So then you will have to equivalent to BFTF, which is this BFTF is again representing your area of flange. Okay, so from that equations, now we know that earlier we already calculated the area of flange is equivalent to 14.660 TF squared. So here, for you to calculate, then you will have the area of flange is equivalent to MED, okay, because that is the MPLRD, MED over HW FYW over aspect ratio. and then submit all the equivalent parameters that we have determined earlier, will give you MED 11.6 times 10 to the power of 9 divided by your HW, we already determined it, 1978 times with 355 over 1.0, and finally you will end up with 16.520 millimeters squared. So then you will get the area of flange here is 16.520 millimeters squared. So what you're going to do next, okay, because earlier you know that the area of flange is 14.66 TF squared. So equivalent, okay, so you do the equivalence whereby you have 14.66 TF is equivalent to the area of flange that you have calculated, which is 16.52. So you can have 16.520, okay, millimeters squared. All right. So then you can have your TF value. Okay. So your TF value, okay, your TF value, just the double check, okay, TF squared. So your TF value, if you calculate 16.520 divided by 14.66 square root, you will end up with your thickness of flange equal to 33.6 mm. Okay, so once you get your thickness of flange 13.6 mm, okay, so then you can submit this value, okay, this value to the earlier equations. Substitute TF into equations earlier, okay, substitute TF into equation earlier, whereby in the equation earlier, total width of flange, which is your B, total width of flange is 14.66 TF. So now your total width of flange B is equivalent to 14.66 TF, 14.66 TF. So then it will 14.66 times with 33.6, which means you will get 492.6 mm. Okay, you get 492.6. So meaning that for your flange, okay, this is, imagine this is the flange plate. Your B, okay, your BF is 492.6 mm, all right, whereby you can round up it to 500 mm. And then the thickness of flange, okay, the thickness of flange is 33.6 mm, where you also can round it up to 35 mm. So now you have done the flange width and the flange thickness. So to summary, okay, so summary for basic dimensioning, okay, you have the thickness of flange, okay, thickness of flange is equivalent to 35 mm, meaning that you propose to be 35 mm, because initially it is 33.6 mm. So then you propose to be 35 mm, and then your total width of flange, so BF, width of flange, is equivalent to initially is 492.6 mm, but we propose it to become 500 mm. Okay, again, this is a proposed value, propose. And then you have the thickness of web, TW, thickness of web, which is equivalent to 9 mm, and we also propose it to be 9 mm. Okay, propose. And the last one is the height of web, which is height of web, whereby we propose it to be 2, because we now propose 35. So 2 times 35 plus 1978. Okay, so the overall height of the height of web is 1978. Okay, and then the total height of plate girder is equivalent to 2 times 35, because our flange is 35. Okay, our flange is 35. 2 times 35 plus 1978 does give you 2048 mm as the overall height, but we propose it to be 2000 millimeter. This is the propose. So in general, in summary, this is the flange, this is your web, this is the flange again. So the flange is 35 mm times 500 mm, while your web is thickness of the web is 9 mm times 1978 mm, and the overall height, including the thickness of the flange, so we got it 2048, but we propose overall we make it as 2000. Okay, we propose 2000 mm.